Hello, everyone. We are live. Sorry we're running a little bit late. We had to reboot our streaming computer, but we are here and we are ready to go. Thank you all so much for joining us today. My name is Matthew. I'm going to be behind the scenes helping to choose questions and manage the discussion. And I'm one of the course instructors for our Coursera course. And we're really excited to have you here today. We've got a bunch of great questions already. Make sure you like and subscribe to our channel and hit the bell so that you hear all of our announcements when we start our live sessions. I'm going to hand this over to Professor Impey, and we will let him get started with questions.
Okay, thanks. Welcome everyone to another live session for the online classes, and let's just get right started.
All right, the video seems to be stuck a little bit, but if the audio is working, oh no, never mind, I think we're good. Okay, so the very first question from one of our live participants is from Atsan, who says, good evening, I would like to learn which science fiction films related to astronomy would you recommend that we watch?
Wow, and there's so many, and there's some, better and worse. There are not a lot that actually are directly related to astronomy, so science fiction sort of spins tales and stories of fictional worlds and may or may not include, real astronomy. So there are a few, of course. If you go back to the classics, you could say 2001, Stanley Kubrick's great classic film, had a lot of good astrophysics, astronomy. It was realistic and also exceptionally well done for its time. I think it was 1968, so the technology was quite basic back then. The Martian is a good movie, more recently, based on a really good book about the ability of us to live on Mars and what happens when it goes wrong. A lot of good astronomy about Mars, planetary geology and planetary science included in that movie. There are not as many movies that are about astronomy per se. There have been some good movies about black holes, and I'm just going to zone out on the name of the best one, the one that...
Possibly Interstellar.
Interstellar, yeah. So Interstellar is the best black hole movie. It had Kip Thorne, a Caltech professor and expert on relativity and black holes, as a scientific advisor, and it, fictionalized the idea of a very massive black hole and what would happen if you were near it. So there's a lot of good astrophysics in that one. So that's a small selection. There are obviously a lot. There's some that, distort the science and the astronomy quite substantially. But I would say another one would be Avatar, which is, fictionalization of the idea of life on the moon of an exoplanet. So there's some good astrobiology in that and some good planetary science. So there are a number of good movies. That last one is James Cameron, and he's done a number of movies that incorporate good science. So there's rich pickings there, and it doesn't have to totally adhere to the science to be good. You don't have to get every little thing right to make a good movie, of course, and still have enough core science.
Excellent. Thanks for those recommendations. World of Science, who is on with us live, asks, what is your say on multiple dimensions, or on dimensions of our universe in general and our understanding of them? Can 4D supercube tesseracts exist?
Well, the conventional description of space-time through general relativity is a four-dimensional manifold. That's the mathematical term for something that can be curved and not simple linear space, where the four dimensions are three of space and one of time, and they're coupled. So the time is coupled to the space in general relativity. They interact with each other, especially in extreme situations of gravity. Any theory that involves higher dimensions or additional dimensions is almost by definition speculative, because we have no direct evidence for that. They are motivated in different ways. One of the motivations for extra dimensions comes from string theory, from the idea of a fundamental theory that goes beyond standard particle physics and somehow manages to incorporate gravity into the equation. And those theories tend to almost always involve multidimensional spacetimes, 9, 10, or 11 dimensions, where the hidden dimensions are essentially compactified on incredibly small scales or very high energies. And there's a whole general class of theories called M theories, where the M stands for membrane. So there's a sort of world of multidimensional space-time models that have not been fully explored. But again, I emphasize they are all speculative. There's no evidence for any of these extra dimensions of space. There are experiments to try and see if they do exist. There are some lab physics type experiments that can probe for extra dimensions, and the way that works is by looking for modifications of the force law, for example, the electromagnetic or gravitational force law on small scales, which might reveal the presence of a hidden dimension or more. None of those has succeeded, so at the moment it sits in the realm of speculation.
Excellent. The next question is from one of our live participants. Chris Matson would like to know, if microbial life was found on Mars or a moon, would it be plausible to assume that intelligent life must exist in the universe somewhere, either close or distant?
That's a good question. It's very hard to tell, and it's very hard to make a firm argument based on a second example of life. It is for sure the case that if a second example of life is found within the solar system, say, it increases the odds that life is widespread in the universe, with a caveat that it is of course possible that life on Mars could be the common origin of life on Earth, that it may still represent a single origin, and then we still only have one instance of life. That would not, however, be true if the life on Mars had a different biological basis, so it's not part of the same tree of life that we see all life on Earth. Now, the inference of intelligent life beyond Earth, if we find another example of microbial life, that's tricky, because some people argue, astronomers and many biologists argue, that the pathway in evolution from microbial life to intelligent life is by no means guaranteed. And as evidence for that, just look at the history of the Earth. On the Earth, it took several billion years. There's been life on Earth for 4 billion years, close to it. And large brains and intelligent creatures and we emerged very late in that history. So there was life on Earth for several billion years with no hint of it becoming more complex, even rising beyond multicellular states and becoming physically large. So it's not therefore inevitable that it would happen. It might take even longer elsewhere, and so might not have happened in the history of the universe. And with only one example of intelligent life, or maybe a few if you include dolphins and orcas and so on, elephants, your favorite animal that might be intelligent and sentient, you have a handful or one species out of hundreds of millions of species on this planet that got to that state. So the fact that it took a long time and happened to a tiny, 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 negligible fraction of the species on Earth suggests that it need not be inevitable. It might actually be a very rare occurrence, even if microbial life is common. Now, that's not a decisive argument, it's just suggestive. But it means that we shouldn't be so sure that intelligent life exists elsewhere if we find one other example of microbial life.
Excellent, thank you. Kind of a follow-up question to the previous question about dimensions. Could an object such as a 4D supercube or tesseract cause changes in time?
Multidimensional space-time theories do also couple those higher spatial dimensions to time in an analogous way to general relativity, although they're fundamentally different theories. So yes, space and time are expected to be coupled in these higher dimensional theories too. Now, the way in which time is altered would of course be quite different from the way it's altered in general relativity. And I don't really think the theories are well enough developed to explore the nature of the distortion of time. So that's sort of up for grabs, because these theories are extremely difficult to calculate in and develop the formalism to make progress. And so I think there's been not much exploration of the time dimension of these multidimensional theories.
Thank you very much. The next question is from Wendy Traver, who always sends great emails. Do you think that planetary protection rules will impede scientific discovery to a significant extent?
I don't think so. Planetary protection rules are first of all, we should recognize that there's no overarching legal framework for planetary protection. In other words, there's no supranational body that regulates planetary protection. The United Nations has only ever passed and had significant numbers of nations sign on to 2 treaties about space. One was the Outer Space Treaty of 1965, which demilitarized space, very importantly. And then the second was the Moon Treaty of 1979, which talked about ownership of space and exploitation of resources. So neither of these treaties talk about planetary protection or the idea of protecting resources or keeping pristine environments off Earth. NASA has taken it upon itself to be active in this area and motivated in a couple of ways. NASA is motivated particularly by protecting the home planet from any alien microbes that we might bring back from Mars or elsewhere by robots or by astronauts. So the planetary protection that NASA worries about in the first instance is protecting us from alien microbes, I guess is the simplest way of putting it. But NASA's also got fairly forward-thinking views on protecting other environments that we might visit with our spacecraft. And it's certainly true that most NASA missions, almost by design, sterilize themselves. They're both sterilized before they leave the Earth, and then they sterilize themselves quite often, especially in the entry to a planetary atmosphere. They're superheated, and so any microbes on the spacecraft would be destroyed. And NASA has gone a little further than that and had a premise that it's not going to litter any planet that we visit with hardware unnecessarily. So planetary protection is a part of what NASA does. They take it quite seriously. But it's not a rule that other countries have to obey. The Chinese are very active in space now and have visited the Moon, plan to visit Mars, and they've not signed on to any protocols about planetary protection, nor have the Russians, nor have any of the other spacefaring powers. So unfortunately, at the moment, planetary protection is just an idea that's out there, and a lot of people in the space science community support the idea of planetary protection. But there's no governing body, and then more importantly, there's no enforcement mechanism behind any of this.
Excellent. The next question is from Art Studio, who's on with us live. How do Bose-Einstein condensates have a strange nature of variable magnetic fields?
So Bose-Einstein concentrates are one of the interesting phenomena of physics. Bose-Einstein statistics is the physics that underlies the behavior of integer spin particles. Photon is an integer spin, it's spin zero essentially. So spin zero particles that obey Bose-Einstein statistics have the ability to have coupled behavior if you create the right physical conditions. And typically those conditions are extreme cold. And so the first Bose-Einstein condensates were created in the physics labs a couple of decades ago. Carl Lyman won the Nobel Prize for this work maybe 20 years ago, 15 years ago. He's now an innovator in science education, so I'm aware of his work in that arena. And so that was Nobel Prize winning research. The role of magnetic fields is often important because it is often by alignment in a magnetic field of charged particles that you're able to create the physical conditions for a Bose-Einstein concentrate. I'm not aware of any spontaneous magnetic field generation mechanisms in concentrates at that level, so that's going a little beyond my physics research knowledge. But they are certainly involved and invoked in the creation of the condensate in the first place.
The next question is from Red Unleasher. Can you briefly talk about how we found the remaining 2.5% of baryonic matter? Yeah, I'll just end it there for now.
Sure. So the behind the question is the issue of where are the baryons in the universe. So baryon is a physics term for heavy particle, and these are normal particles that make up the matter we're made of, protons and neutrons typically, which themselves are made of quarks, which are also massive particles. And so the question is, were we able to find most of the baryonic material in the universe? And for some decades, it's been clear that we could not identify it because there was a disconnect between two things. The theory of baryon creation in the universe, the Big Bang theory, pretty much predicts that about 4% of the universe should be baryonic material. But when we do an inventory in the local universe of all the stars and galaxies, all the way down to the end of the stellar mass sequence, we don't uncover 4% of the universe that way. We uncover less than 1%, actually, more like 0.5%, all the stars and galaxies. So that's a huge mismatch. We're missing 80 to 90% of the baryons, and the question is, what form are they in? And the answer is, of course, they can't be in the form of normal stars in galaxies. They have to be in some darker, harder to find form. And in a series of research initiatives over the last decade or so, people pretty much think they've identified these missing baryons, as they've been called, and they're in the intergalactic medium. So they're distributed on much larger scales than galaxies themselves or stars. And they're in a very interesting physical state. They're far from stars, and so they're not illuminated by starlight, and that's why they might be dark. Yet, despite being in a very diffuse, near vacuum state, they are actually at a very high temperature. And so they were first detected in X-rays, and by X-ray absorption, and by clever X-ray shadowing experiments, because this plasma, this very high temperature, low density intergalactic medium, in fact contains the missing baryons, and it's thinly distributed through space. If you could make images of it, and there have been a few attempts to even image this medium, you can see that it would have this web-like structure, so-called cosmic web, because this is the relic of where structures form in the universe. And in the space between galaxies, even though there are no galaxies, gravity does turn this medium into a sort of semi-collapsed set of string-like networks in 3 dimensions. And so that's called the cosmic web, and it's the repository of the missing baryons, and those missing baryons are at very high temperature. They're temperature of a few million or certainly hundreds of thousands of Kelvin, and so if they would emit any radiation, it would be soft X-rays, hard ultraviolet. That's very hard for astronomers to detect, but we have had some success. The question of why this medium, far from galaxies and stars, is so hot is because it's been irradiated by all the light from galaxies over cosmic time, which does penetrate intergalactic space and will slowly but methodically heat up this medium. And because the medium is very rarefied and low density, it can actually have a very high kinetic temperature. And so this is the case of the missing baryons, and they pretty much have been identified and found at this point.
Excellent, thank you very much. The next question is kind of a related follow-up. Can you talk a little bit about what the Lyman alpha transition is that was used to achieve this discovery about the 2.5% missing baryonic matter,
right,
and what technology was used to find this Lyman alpha transmission?
Yeah, the Lyman alpha transmission is transition rather is a spectral line of the hydrogen atom. Remember, hydrogen is the most abundant atom in space, and this is the signature. You look for spectral signatures of the elements, and if you have a material that's very high temperature, then it's going to have these transitions that are in the ultraviolet. And the Lyman alpha transition is an energy state 2-to-1 transition of the innermost and therefore the most energetic shell of electrons in a hydrogen atom. And the wavelength of that transition and the Lyman limit, or the Lyman alpha line, is 1216 angstroms. So that's 100 nanometers essentially. So that's very short wavelength. That's 5 or 6 times shorter wavelength than visible light, and so it's ultraviolet. And so basically the method used was to take spectra using quasars as flashlights. Quasars at large distances will illuminate the intergalactic medium, just sending a stream of photons towards the Earth, and this gas will, through the Lyman alpha transition, will absorb radiation at this wavelength, this ultraviolet wavelength. So you need an ultraviolet spectrum to see these lines and to detect this medium. And the best tool for that has been a series of small space missions, and then of course the Hubble Space Telescope, which has had a very powerful ultraviolet spectrograph for some years. And so that's where this work has been done, with ultraviolet spectroscopy.
Excellent, thank you very much. The next question is from Hernan, who's joining us from France, as always. Thank you for Coming again. We got this via email, and the question is essentially about Triton. That's a moon that's not really often discussed, and it has some kind of strange properties, and some people consider it to be a captured Kuiper Belt object. What do you think is the astrobiological potential for a moon like Triton, and is it worth exploring for astrobiology?
Yes, Triton is a very interesting object. I'm not a planetary scientist, but I know something about Triton just because it's one of the more fascinating moons in the solar system. This is a moon of Neptune, and it's really only been directly explored by one space probe, the Voyager 2 probe. So we don't know as much about it as we'd like. There have not been that many missions to the outer solar system objects. It has a retrograde orbit, so it's a moon in a retrograde orbit, which suggests strongly that it was captured from elsewhere. And so there's the hypothesis that since we're in the outer region of the solar system, it was captured from the Kuiper Belt, which runs from about 40 to 100 astronomical units, so from near where Neptune's orbit is, out by a factor of 2 or 3. That doesn't explain everything about Triton's orbit, but I think it's a plausible hypothesis that it was captured. And certainly its orbital properties currently do not make it seem sensible that it was formed where it sits now. The process of circularizing its orbit, assuming it was captured, is interesting because it's led to quite a lot of tidal heating. And so it's a fairly large moon. I can't remember its rank, but I think it's in the top 10, maybe 6th or 7th largest moon in the solar system. So pretty substantial sized moon. So, because it's substantial in size, it has substantial internal heating from radioactive decay, and it's had a substantial amount of tidal heating from the circularization of its orbit in a captured orbit, and that has helped to heat the interior. So, given its distance from the Sun, there's a substantial amount of available heat. We know spectroscopically and from study of the surface that the surface regions, the crust and maybe into the mantle of Triton, is about 1/3 water ice, which is quite a lot. So it's a rocky, icy body with a substantial amount of water ice. And even though we can't prove it, there's strong speculation based on the internal heating that we expect and know must be there, that there is subsurface water, perhaps liquid oceans or seas under the surface where we can't see them, kept liquid by internal heat, by tidal heating, and by pressure from the rock and ice on top. So it's very plausible, therefore, that Triton is as good a astrobiological target as any moon in the outer solar system that has liquid water, because it has all the ingredients for life. There's a local energy source, there's liquid water in places, and there's plenty of carbon-rich material. So I'd say yes, it's a very good astrobiological target. There's maybe a dozen moons in the outer solar system that fit this bill. Ganymede would be another example, a much bigger moon. And the trouble is we have very limited information. We'd actually have to send a new space probe there to learn a lot more. There's just not much you can do with telescopes since it's so far away. But astrobiology is looking at these targets, not just the inner solar system and not just moons of Jupiter and Saturn, but also some of these outer solar system moons.
Excellent. The next question is from Steve McFadden. What would you say are the most important physics concepts for aspiring astronomers? I'm interested in the formation of planetary systems, so I want to focus on the most relevant aspects of physics.
Yeah, so generally for physics, for astronomers almost always have a base coat of paint and training in physics, and typically have an undergraduate degree in physics. I do, and most professional astronomers started in physics. As far as the physics that you actually will use if you become an astronomer, and in particular a planetary scientist, you need the basic foundational conservation of energy, conservation of angular momentum, because these come into play when you're considering the formation of solar systems. You also need to know about the formation of different mineral elements and refractories as a function of temperature in the solar nebula, because knowing the temperatures at which different chemical compounds and elements both solidify or liquefy gives a sign for what bodies in a forming solar system could have large amounts of frozen volatile materials, including water ice and carbon dioxide ice, and methane ice as well. So their refractory elements and their condensation temperature is another important piece of physics that you need to understand planetary systems. Also, there's some geological principles. You'd need to know the geological principles that lead to the requirement for tectonic activity for the liquid core of a planet or a moon based on its mass and its chemical composition. The likelihood that it will have water and how that water derives from, where it comes from, whether it was originally in the formation or was deposited afterwards. So there's sort of geophysical principles that apply now in planetary science, because we're starting to consider exoplanets as geophysical worlds, not just as objects with a mass and a size, and that's all we know about them. So in planetary science, there's a lot of information like this. You also need to know about magnetic fields, because the role of magnetic fields in planets is important. They can act, as in the case of the Earth, as a shield against solar wind and possibly an increased probability of maintaining life on a planet. So the formation process by dynamo mechanism for magnetic fields in planets, that's another important piece of physics that planetary scientists need to know. So there's quite a lot of physics involved in planetary science, in fact. And planetary scientists have their own physics class. If you go to graduate school in planetary science, you'll be continuing to take a few graduate level physics classes before you get your master's or PhD.
Excellent, thank you very much. The next question is from Art Studio. Could there be another world made up wholly of antimatter?
It's always possible in principle, so theoretically we can imagine it, but in practice I think not, because antimatter is incredibly rare in the universe as far as we've inspected it. We know how antimatter can be created from pure energy. Equal numbers of particles and antiparticles can be created. That's a standard mechanism. So if you had a lot of energy, you could create large amounts of antimatter. For example, very early in the universe, in the Big Bang, there were equal amounts of matter and antimatter. But that situation only persisted for a fraction of a second before the particles and antiparticles annihilated, and a small residue of particles were left over to form all the stuff of the universe. Everywhere we've looked elsewhere for antimatter, we have not found it. And so we've not seen anti-planets or anti-stars or anti-galaxies. And the reason we know this, antimatter doesn't mark itself out as having an opposite set of quantum properties. The only way we really know about it is by looking for the adjacency. Antimatter, when it comes into contact with matter, will of course annihilate and create radiation. So it's very hard to hide any types of antimatter in the universe, because at some point, even in the space between stars or galaxies, antimatter will encounter normal matter and lead to gamma ray emission. And we've had sensitive gamma ray telescopes now in space for decades that would have seen antimatter if it existed in any significant amount. So basically, it looks like the universe is almost overwhelmingly made of matter.
The next question is from Robert Brady. Is it possible that the Big Bang was not symmetrical? Could it have had lobes? Could it have had one lobe of antimatter and one lobe of matter? What are the possibilities for an asymmetric expansion of the universe from the Big Bang?
So it's an interesting speculation. Could the Big Bang have been non-symmetric in some way? The reason it's not likely is because any asymmetry in the early expansion would map into the older, larger, lower temperature universe. And we have a very strong evidence from observation that the universe is isotropic and homogeneous. This is called the cosmological principle, in fact. Homogeneous means it's more or less the same at any location of space, and that really just means that when we look out, we see roughly the same types of galaxies that we do near the Milky Way and other regions of space. But for asymmetry purposes, isotropy is a more important constraint, and that basically means if we point our telescopes out in any direction to the limit, to like the Hubble Deep Field limit, and count galaxies or look for structures or look at the amount of radiation or the temperature or anything we can measure, isotropy is seen, which means that the properties do not vary depending on which region you look out in space. And so if the universe had been asymmetric, And we're probing back a good fraction of the way to the Big Bang. Maybe not right to the beginning, but with the microwave radiation, we're probing within 400,000 years of the Big Bang. And there's no sign of anisotropy on any significant scale. So therefore, it's unlikely that the Big Bang itself was asymmetric.
Another question from a live participant. Keith would like to know the new book or article from Avi Loeb is still kind of in the news about Oumuamua. Can you talk about your thoughts on this and about the Starshot project ultimately?
Yeah, I mean, I'll treat those as two separate questions because they're kind of different topics. So Avi Loeb's book has caused quite a big splash. He's taken what was a research paper with a postdoc of his from a couple of years ago and turned it into a book where he argues that Oumuamua is an alien artifact, essentially, and not a naturally occurring object that came into the inner solar system. And he's basing this largely on its orbital properties, on its speed and its trajectory into the inner solar system. And he's inferring, because we can't measure it, that the object is essentially a light sail. Then that's why it is an alien artifact. It's not a naturally occurring, even very skinny asteroid. He thinks it's actually very thin and almost two-dimensional. There's no evidence for that. The orbital properties are indeed unusual, but people have countered his contention and said that they don't require an extreme hypothesis, and that's a pretty extreme hypothesis to explain a otherwise pretty pedestrian object. So it's sometimes not clear whether he's being controversial just to be controversial. He's a very smart guy and he knows how to make an argument, but he's also pushing his argument pretty much to the limit in contravention to more conventional interpretations that are simply not ruled out at this point. So if I was betting, I would not bet on this being an alien artifact. And I haven't read his book yet. I read the original article a few years ago. I'll probably read the book when I can. So that's a provocative piece of writing by a well-known astrophysicist. And Loeb is part of the Project Starshot. So Project Starshot is an adventure that was announced with great publicity a few years ago to harness cutting-edge terrestrial technologies to send a fleet of nanobots to explore the nearest stellar system, Proxima Centauri. In a nutshell, the idea is to use incredibly powerful lasers to focus their radiation on a tiny miniaturized spacecraft with solar sails attached, the roughly meter-sized solar sails, and use that radiation to accelerate those tiny probes to 5% of the speed of light, perhaps, at which point it would take 1.5 generations to reach Proxima Centauri. And then there'd have to be a reverse process to decelerate them, and it's not clear how you would arrange that at the other end. That's a problem, actually. But these probes will have sensors, and the idea is to find what is hypothesized to be terrestrial planets in the Proxima Centauri system. That's up for some debate still at the moment, whether these exist, but there's a good bet that they might. And then do direct exploration of a Earth-like exoplanet in a nearby star system. Very exciting project, of course. And it's funded initially by $100 million from Yuri Milner, a Russian industrialist who also gave $100 million to SETI a year later, I think. So a very wealthy billionaire is willing to put a lot of money into space science projects. Avi Loeb is one of the board of directors, I think. Stephen Hawking was until his death, and various other, well-known astrophysicists. So it's got a very elite team of scientists involved advising it, and it's got some very clever engineers trying to work out these technologies. And if you were to ask them or check out their website, they will claim that they're about a decade away from being able to realize this experiment.
Excellent, thank you. Tyann, who's on with us live, or Tian, would like to know, theoretically, if dark matter falls into a black hole, would that help us know what it is and how to make, but would that tell us anything about black holes or about what dark matter is?
That's an interesting question. Dark matter, if dark matter falls into a black hole, it's just obeying the gravity based on the mass of the particle, and we think it's a dark matter fundamental particle. So dark matter falling into a black hole essentially represents fundamental subatomic particles of unknown nature falling into a black hole. Now, normally, if a charged particle was accelerated and falling into a black hole in a presence of a magnetic field, which exists around black holes, we'd see it radiate, synchrotron radiation, for example, if it was electrons. But dark matter particles are not going to be charged, so there's no signature they would give as they accelerate towards the black hole. And in a sense, it's really going to be hard to know what's going on. So the falling in of dark matter into a black hole does not itself lead to any tracers to tell you what the dark matter was. And once the dark matter is inside the black hole, of course the black hole will grow in mass, but at a level and at a rate which is very hard to measure astronomically. So we won't really even be able to measure the addition in mass rate from the dark matter unless somehow it was a large influx of dark matter. So unfortunately, although it's a nice idea, I don't know that we can use black holes as little labs or experiments to tell us more about dark matter.
Excellent. Thank you very much. The next question is from one of our online participants. When do you think that humanity would be able to start building something like a Dyson Sphere?
Well, Dyson Sphere is, so that everyone knows, Freeman Dyson, 95 now, I think, just a very famous astrophysicist, had his hand in a lot of things, and he gave the term to the idea that an advanced civilization, if it wanted to be more energy efficient of the energy from its star. Remember, the Earth intercepts about 1/billionth of the sun's radiation, which of course goes out in all directions into space, and of that 1/billionth of the sun's radiation that hits the Earth, we of course harness another tiny fraction, so maybe 1/trillionth of the sun's radiation is used by humanity to fuel its civilization. Of course, most of the time we're relying on it for our energy on fossilized fuel, so it's not really solar radiation itself. But even if we were to become solar self-sufficient, we'd be harnessing a very tiny fraction of sunlight. A Dyson sphere is an object that a civilization constructs physically around a star, near the star, that traps a substantial fraction of its energy. So instead of intercepting 1/billionth, you trap a good fraction of the total light of the star. So obviously you've increased your energy capture by factors of millions or tens or hundreds of millions. Now it's easy to visualize this as an actual sphere, coated with solar panels or some advanced technology to convert the sunlight into energy and then beam it to the planet that's still far away. So this is just a tool a civilization would create around its star and then beam the energy to where it needed it. It can't be a solid object because differential rotation means that it would break apart. So a Dyson sphere has to be a sort of quasi-flexible thing, and so it wouldn't be a completely filled surface of a sphere. That wouldn't work at all. Engineers have commented on what kind of construction a Dyson sphere would be. As for how far away we are from creating such a thing, we have trouble, just imagining a moon base in the next 10 or 15 years, and that's an object that's 250,000 miles away. If you're talking about the sun, that's 100 million miles away, and working in that intense environment and doing a physical construction project where you'd have to mine the material, I presume, from Mercury or somewhere closer, or whatever material you needed to distill down to make your construction material, that's an incredible undertaking. So I'm going to say, it's hard to put a number on it, I'm going to say we're centuries and maybe millennia away from being able to make a Dyson sphere.
The next question is from Arnold Ginsberg, who would like to know when can we expect the first photos of the black hole in the center of our own Milky Way galaxy?
That's a good question, and I'm going to guess possibly this year. It was known at the time that the Event Horizon Telescope produced a spectacular image of M87, which is a massive black hole, 6 billion solar mass black hole in a galaxy that's tens of millions of light years away, that the next best target for making an image of the event horizon would be the Milky Way at the center of our galaxy. So that black hole is roughly 1,000 times less massive than the Milky Way, than the black hole in M87, and in the scaling relations of black holes, the event horizon size scales with the mass. So the black hole will be 1,000 times smaller than the M87 black hole. But the center of our galaxy is just under 30,000 light years away. And that, of course, is roughly 1,000 times closer than M87. So if you see the trade-off, it's just about as easy to make an image of the black hole in the center of our galaxy as it is the M87 black hole. Turns out to be slightly harder, and that's why it was the second bet rather than the first bet. But I'm sure I know they've gathered data already on the Milky Way black hole, and it's not beyond the capability of the Event Horizon Telescope, so I'm anticipating that discovery and result to be announced later this year.
That is spectacular. I'm excited about that, and we'll have lots to talk about when that happens. The next question is from David Gold. What star or constellation or constellations did explorers in the southern hemisphere use for navigation?
Well, so they didn't have an analog of the pole star. So we have, Big Dipper, Little Dipper. We have a pointer star to get us to due north, and that aids navigation enormously. The analog, there's no equivalently bright star to Polaris at the south galactic, at the center of the south galactic pole, the region around which the Earth appears to rotate, or the sky rotates as the Earth rotates. Navigators in the southern hemisphere essentially use the Southern Cross. You can project one of the arms of the Southern Cross by, I think it's 3 times its dimension, and that puts you to due south. And so that's a pretty easy reckoning device for any navigator in the southern hemisphere. And I think that's the main way they navigated in the south.
Excellent. One of our live participants, Jorge, would like to know, could you comment on the influence of radioactivity during the first billion years of life on Earth? Based on heavy elements half-life, it must have been considerably higher than today. Could this have been an issue?
Yes, there has indeed been a history of radioactivity on the Earth that has declined, and also a history of impacts which would have affected life and its evolution. Those impacts also declined, so the ferocity of catastrophic impacts declined. And as the Earth cooled, and as the heavy material sunk to the center of the Earth, then that radioactive material was taken out of its situation in the crust or near the crust. And so, especially in the first 100 to 200 million years after the Earth formed, the ambient radioactivity rate must have declined substantially. Now, we don't think life started that early. So the question is, did early radioactivity on the Earth, say in the first billion or so years, impede or have any effect on the evolution of life? And the answer is probably not, because there's no indication in their oldest microfossils or rocks that we have available to us. So we have rocks we can date to 4 billion, 3.5, 3 billion years, and there's no indication that the ambient radioactivity is substantially higher than it is now. Somewhat higher, but not enormously higher. And there's therefore no indication that microbial life would have been extremely adversely affected. Higher radioactivity does indeed increase the mutation rate. So the natural mutation rate for the earliest microbes might have been higher, induced by radioactivity. Mutation is not always a bad thing for microbes, as we're learning to our cost in the pandemic. The mutation of viruses actually helps them spread, evolve, adapt, and reach other environments where they can thrive. So radioactivity and mutation is not a bad thing necessarily, and so it probably was elevated in that first billion years.
The next question is from one of our live participants. Tony Gojinovic would like to know, is the era of a solitary genius no longer a thing? Is it over, such as an Einstein or a Galileo?
And that's a good question, and historians and scientists, debate that often. The idea of how science works now, and is the age of the lone genius over? Statistically, yes, it is, because the evidence of the last half century, and there's been papers written about this in the last decade or so, is that the growth of large teams in science is a very dominant effect. And so the team size in biology and physics and chemistry and my subject has been growing steadily. Most research is now done by teams, and often they're large teams. In high energy physics, there are teams of now thousands. It used to be only hundreds. Astronomy still has teams of dozens, but it has teams of hundreds as well. There's also interesting work in the scholarly area called science of science that has shown that large teams are less likely to innovate, that the more supple ideas come from either sole investigators or small teams. That shouldn't really surprise us, that groupthink in a large team will sort of squash innovation or radical ideas. So the growth of large teams sort of is mitigating against the impact of sole geniuses, because where are they? In experimental and observational science, the hardware and the tools are now so expensive and so hard for any individual to muster or harness that people almost have to work in teams. In theoretical work, it is still possible to work on your own. And so the exception to this, and the fact that there still could be sole geniuses transforming a subject, is that in theoretical science, you can do great work individually, and many people still do. So I say that at that age of the sole genius, I don't think we should declare it over yet. Obviously, people like Einstein and Newton and Hawking say they really don't come along very often, but there's probably the young version of the next Newton, Einstein, or Hawking, and let's hope or imagine it's a woman this time. Why not? There are more women doing science than there ever have been. Are still going to exist. So I don't think that's over, that individuals, when they're extremely smart and perceptive, can gestate ideas that are unique to them and that don't necessarily bubble up from a group setting or from the work of a bunch of scientists in harness.
So there's kind of an interesting discussion going on in the chat right now, so I'm going to jump past a couple of other questions just to address it. There's a discussion kind of about Einstein's equations and sort of the evidence for the Big Bang Theory. And the question is it possible to solve a basic three-body problem, like a gravitational problem, planetary motion problem, using Einsteinian field theory?
Yes, but only approximately. So with Einstein field theory, as with classical Newtonian mechanics, there's no exact solution for three or more objects. There are numerical approximations that you can use, and you can, of course, calculate that these days with computers to almost arbitrary precision, but they're not absolute solutions. And then the same is true in general relativity. In terms of the metric of space-time, which is sort of fundamental description of space-time in any astrophysical situation, there have really only been a handful of metrics that have been formally completely defined, that is to say, completely defined by equations without any approximation. And for example, the static black hole and a spinning black hole are two of them. It's really very rare that general relativity is soluble exactly through its equations for any realistic astrophysical situation. And in three-body situations, it's not soluble exactly. So people use numerical methods, numerical general relativity essentially, done with computers.
And then, am I correct in remembering that if you solve Einstein's equations, they eventually, they eventually come down to Newtonian physics? I mean, you get Newtonian physics out of those. So, the reason that we use Newton to figure out trajectories for spacecraft is not because Einstein doesn't work for that. Can you talk a little bit about that?
Right. So the question of when do you use Newtonian gravity and when do you use general relativity, that's a good question. And it's an important question because general relativity is a challenging theory, difficult to work with. And basically, it's the strength of the gravity. That's all, the local gravity. If you're dealing with situations where the local gravity is strong, then Newton's theory fails. That's what relativity was designed to deal with. It's a fundamentally different paradigm. It is easier to calculate in a Newtonian situation or Newtonian framework. And for solar system dynamics and low mass objects, you simply don't need general relativity, and you're making life very difficult for yourself to use it. But if you're talking about dense objects, compact objects, neutron stars, white dwarfs, even black holes for sure, then you have to use general relativity regardless. And also, if the local gravity is essentially the local gravity of the entire universe, like in the Big Bang, then you also clearly have to use general relativity. So those are the situations where you have to use it, and mostly you don't, and most astrophysics calculations do not incorporate general relativity. For example, the people who do simulations of structure in the universe and put particles into computers that are mimicking entire galaxies or all the stars in a galaxy or a set of galaxies in a cluster, they do not have to use general relativity. Newtonian calculation is sufficient.
All right, the next question, and it's 10:55, so we have a few more minutes for questions, but the next one is from Talion Tales. There's very exciting a mission coming up, the landing of Mars Perseverance rover. Can you talk a little bit about the technology behind it and what kind of results we can expect from that mission, which is going to land in just a couple of weeks?
That's right. This is a big month. February is a big month for Mars because in addition to the NASA's Perseverance rover, there's a Chinese mission and a mission from the United Arab Emirates, which is an orbiter. The Chinese mission is challenging because it's a trifecta. They're having an orbiter, a lander, and a rover. So this is the Chinese stating their claim big time on planetary science by doing a very ambitious mission. A lot of attention is on the Mars Perseverance rover, of course. This is essentially a twin, a knockoff, if you like, of the Curiosity rover, and that saved them a lot on hardware development costs because that rover has been tried and tested and has been roaming around on Mars for years now. What's new, of course, about Perseverance is the instruments aboard. And while Curiosity was not really able to directly test for life, was just essentially doing geomorphology and geochemistry experiments, the Mars rover, the new Mars rover, has a set of, I think, 7 instruments, which does include real attempts to look for the tracers of life. Now, it's not full-on PCR, polymer chain reaction, replication of DNA fragments to see if there's actual living organisms on Mars, because nobody expects living organisms on the surface of Mars, which is all this rover can do. It can dig very modest amounts into the soil, some centimeters, but that's not a distance where we would expect living microbes. That soil is sterilized essentially by hard radiation coming through the thin atmosphere. So this is a rover designed to look for the traces of life. It's landing in a region that was a river delta, which probably had sedimentary rocks, and which, of course, could have had microbes 1 billion, maybe 2 billion years ago. So it's going to be looking at the geochemistry of rocks using lasers and mass spectrographs built into the instrument, so they can vaporize rocks and essentially see what all the chemical ingredients are and look for quite complex molecules. It's going to look for the molecules that are associated with biology on Earth if we looked in rocks for fossilized life forms, for example. It doesn't expect really to identify fossils through its cameras. That would be amazing. I mean, it will be looking, of course, for microfossils. But the most interesting information is going to come from a spectral analysis of vaporized rock samples from the surface to look for the kind of complex molecules that we see on Earth only associated with biology, as a residue of biology, as a byproduct of metabolism at work, and so on. It's going to be difficult to interpret this data, and so, there may be ambiguity in what it finds. It may not find any kind of smoking gun for life, previous life on Mars, but it's raising the game, if you like, of looking for life on Mars to an entirely new level, and therefore very exciting.
The next question is from Yang Kao. Do we define intelligent life by reference to the brain, or I guess I'll say more generally by biology, or by the detection of technology?
And it's a good question, and people have noted, including people who do this work, that SETI, the Search for Extraterrestrial Intelligence, is actually misnamed as an acronym. It's really the Search for Extraterrestrial Technology. It's SETT, not SETI, because SETI is only looking for, and can at the moment only look for, artificial radio or optical signals that we think were generated by an intelligent species operating a civilization. So yes, we do not look for intelligence directly in astronomy. We look for technological tracers of intelligent life forms. We don't even know how to define intelligence very well on the Earth. Where do you draw the line of the various species on Earth as far as intelligence and sentience goes, if you consider dolphins and orcas and elephants and so on? Only we are able to do space travel and build telescopes, but does that mean we should be insensitive to other forms of intelligent life that don't know how to do that? So yes, we don't know how to search for intelligence elsewhere in the universe, and we don't even really know how to define it very well. And so we're left looking for technological signatures that are familiar to us. There may be technologies, of course, that are unfamiliar to us, and we wouldn't even know them if we saw them. And so it's another limitation of this experiment that we're trying to do.
The next question is from NAF Jam. Will the magnetic field of the Earth reverse its direction in the future, and will that cause problems?
Yes, the cycle of 22,000 years for the magnetic field reversal seems to have pertained for a long period of time, and we expect it to continue. It's a well way ahead. It's a whole civilization time ahead of us. Yes, at the point where the Earth's magnetic field resets, the dynamo effect in the liquid core, can dissipate the field and it then has to reform, the Earth loses its protective blanket. The magnetic field of the Earth is a shield against solar wind and cosmic rays. And so there would be a period of time, maybe a few centuries up to a millennium, where the Earth is fairly exposed to high energy radiation, and based on the absence of the magnetic field or its dissipation, the mutation rate for biological tissues on the Earth's surface will spike, will go up by factors of 10 or maybe 100, and that could be quite devastating. Advanced technology and civilizations will be able to shield themselves from these radiations, but not all other forms of life.
All right, we have time, I think, for one final question, and we're going to take this one, and it's from Spacetime with Daniel, and they would like to know if you think it will be possible to build some kind of nanobot that will approach the speed of light, and sort of like Breakthrough Starshot is trying to do, but what are the challenges with trying to make something, even something that small, go that fast?
Yeah, so for nanobots acting as probes and accelerated to significant fraction of the speed of light, the energy requirement is strong. The energy requirement to accelerate a spacecraft containing people is impossible at this point. I mean, it's more than the energy requirement of the Earth for a decade, if you like, to do that for one spacecraft. So you have to go small because the energy is needed, and the smaller the better. So it depends on the degree of miniaturization, I would say. The Breakthrough Starshot model of a nanobot with a solar sail attached, accelerated by a pulsed laser or beamed microwave radiation, that's a good model because we can make terawatt pulsed energy, and a solar sail will harness that energy and accelerate quite swiftly. The nanobot size pretty much has to be a gram or smaller. So Breakthrough Starshot's model is roughly a gram for the nanobot, and that, of course, is miniaturized to have a complete sensor package, to have a tiny imager, to have a chemical sensor, to have magnetic field sensor. It's quite impressive what you can get, even now, into a package about that small. But I'm going to say that we'd have to go smaller still on the nanobots to really realistically get them going any fraction of light speed with current technology. And there's no reason why that could not happen. Miniaturization of sensor technology has progressed incredibly quickly, and essentially by molecular scale engineering, you can create sensors that are down at the level of the scale of maybe 1,000 or 100 atoms in size, and so you can make an incredibly small package. So I would say it's not implausible eventually to have milligram and maybe even eventually microgram sensor packages, and then you could definitely get to a fraction of the speed of light. That's an interesting question to end with. Thanks very much, as always, for the variety, and we have our next one scheduled already for next week, so I'll see you then. And thanks to
Excellent.
Matthew for facilitating, and Alexander for getting us out of a little technical problem earlier. And I'll say goodbye.
Yeah, we had a great number of people here today. Again, make sure you like our video and subscribe and hit the bell so you get those reminders. A couple people have mentioned the class that we've discussed that we're going to be releasing. We don't have a specific date for the release of this upcoming class. I don't know if you want to say anything real quickly about the next Coursera course, but
Sure. So we are working on, we've filmed all the video, constructing the materials, the evaluation materials now. It'll be a course on the history and philosophy of astronomy. So, you know, a little bit of overlap with the existing course, but a lot more sort of thought-provoking philosophical stuff and more exact and more direct history all the way from the Greeks through the modern age. So I'm excited about that course. It's quite a lot of work to put up a course on Coursera, and so we're realistically aiming to launch in May. I wouldn't put a date on it yet, but that's roughly when it'll happen, and we'll give plenty of heads up through our various channels to when that's going to happen.
All right, thank you, everybody. We will see you next week on our stream. That will be on Twitch, and we hope you have a great rest of your week and weekend. Take care.